This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is mechanical power, torque, and rotational speed. Our objective is to describe mechanical power produced by rotating actuators like motors in terms of the measurable quantities torque and rotational speed. This lecture operates under the presumption that viewers watch the Motor Family Tree lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Additionally, this lecture presumes the viewer has a basic familiarity with AC power and three-phase AC. If you're a little rusty on these subjects, not to worry. Guidance will be provided to perform our three-phase AC power calculations during the course of this lecture. First and foremost of our tasks is to introduce and define an extremely misunderstood, or at least by most individuals with a primary electrical background, means of measuring rotational mechanical force, namely torque. Torque is a twisting force. Force applied linearly for people of reasonable intelligence is very easy to visualize. Twisting, not so much. For linear applications, it's easy to imagine pushing, pulling, or moving an object that weighs or otherwise resists you a certain amount, be it in units of pounds, force, or newtons, over a certain distance, be it in unit of feet or meters. At the time you stop moving the object, you sit back, crack a cold one, and say, "I've done work today." By using the term work, it means you've put a certain amount of energy into a system. That energy is measurable as force times distance, expressed in units of foot-pounds force or newton meters, where a newton meter can easily be converted to joules, where 1 joule is 1 newton of force expressed for a distance of 1 meter. If I move an object that resists me with 800 newtons of force, a distance of 3 meters, this means I put 800 newtons times 3 meters, or 2,400 newton meters into the system. If a joule is equivalent to a newton meter, this is equivalent to 2,400 joules. Additionally, using engineering prefixes, I can write this as 2.4 kilojoules. This should be pretty easy. Scenarios involving linear applications of force are featured prominently in the Hydraulics and Electrical Controlled Hydraulic Systems playlist that deals primarily with a linear hydraulic actuator called cylinder. Now along comes a rotating actuator in the form of an electric motor that's driving a shaft that's revolving at a high rate of speed, but it's not really going anywhere. There's some obvious force behind that spinning shaft because rotating actuators like drills, blenders, saws, and grinders readily transform durable objects into dust. But how is all this measurable, quantifiable, and somehow comparable to our previous description of linear mechanical energy? My recommendation is to keep thinking linearly. Imagine, if you will, a winch with a rotating shaft that has a radius r. This shaft has a magic rope hooked to it. The magic rope doesn't weigh anything, nor does it have any thickness or stretch or break or give you rope burns or do any of the other things normal ropes do, except pull. That rope is attached to an object that weighs or otherwise resists movement, a quantity of force, being units of pounds force or newtons. Now, spin the shaft 1 full revolution. Aha! Some of you are already seeing where I'm going with this. Before we take this concept home, let's return to the concept of twisting. You're no doubt aware of a simple machine known as a lever. Levers make it easy to apply force because of their length. A longer lever will produce more torque given the same input. Don't believe me? Take that big old $200 textbook you never open, put it in one hand, and hold it close to your chest. Not so hard. Now extend your arm fully horizontally and keep it there. A little different, huh? There's more torque because that identical force is being applied with a longer lever. This twisting force is called torque, and it's directly proportional to both the force applied and the distance from the center of the circular arc it's trying to describe. Granted, with this textbook example, you've got gravity in there, and eventually that circular path isn't so circular. But for now, think of just that brief arc where the force is torquing your arms in a circular path. If that same torque is applied continuously along a complete circular path, it would act tangentially at every point. What does tangentially mean? It means like a stone from a sling. If we release the stone at any point, it flies tangential to the circular path and smashes through your neighbor's window. Yes, there's a good story behind that one. Getting back to the point of torque being proportional to both force and radius, we get the formula torque equals force times radius. Longer lever, more torque. Smaller lever, less torque. More force, more torque. Less force, less torque. Commonly used units of torque would be foot-pounds force, inch-pounds force, or Newton meters. Notice the similarity of units with that of energy. Torque is not energy. It's still torque, despite the commonality in units. For those with a vector physics background, you realize energy is a scalar quantity, i.e. one that has magnitude but no direction, whereas torque is a vector quantity, something with both magnitude and direction. The magnitude of torque may be the same at any given point in the circular path. However, a sling stone cast at points 180 degrees opposite of each other would cast the stone in two opposite directions, which is kind of the punchline to my sling stone through the neighbor's window story. Returning to our linear winch example, when a motor pulls the object toward it with a constant velocity and the load is neither accelerating nor decelerating, the winch will be producing torque equal to force times radius. Now consider the work or energy put into the system when the shaft turns one full revolution. From the perspective of the object, energy input to the system is force times distance, because the object representing a resistance force moved a certain distance. It should be very easy to figure out that the distance traveled by the object is equal to the amount of magic rope that got wound around the perimeter of the shaft when the shaft revolves one turn. The perimeter of the shaft is 2 pi times the radius. If the distance equals 2 pi times the radius, and energy is equal to force times distance, then we can substitute this definition of distance into our energy equation, where energy now equals to force times 2 pi radius. Knowing our earlier definition of torque is equal to force times radius, we can rearrange this equation to make it easier to spot a place where we can substitute torque. Ultimately, we can say energy for one full revolution of the shaft is equal to 2 pi times torque. This means every revolution of a shaft producing a given amount of torque delivers 2 pi torque of energy in units of joules. Ta-da! That's how torque is used to describe energy input to a system. Let's try an illustrated example of this concept. Consider a 2,000 Newton force being exerted on a rope that is wound around a shaft with a radius of 25 millimeters. How much torque does the shaft exert? Torque is force times radius. 2,000 newtons times 25 millimeters, or 0.025 meters, yields 50 Newton meters of torque. How much energy is imparted to this system for every single revolution? Energy is equal to 2 pi times torque. Every turn of the shaft should impart 2 pi times torque of energy into the system. 2 pi times 50 Newton meters is 314.2 joules. Let's say the shaft is revolved 1,700 times. How much energy is imparted to this system with 1,700 turns of the shaft? 314.2 joules per turn times 1,700 turns yields roughly 534.1 kilojoules. You think these shortcuts are too easy? One can always use alternate methods to confirm these results. With a shaft radius of 25 millimeters, a single turn of the shaft revolves 2 pi times 25 millimeters, or roughly 157.1 millimeters of rope onto the shaft, tugging that 2,000 Newton object 157.1 millimeters closer. If the shaft turned 1,700 times, it means it's pulled that object 1,700 times 157.1 millimeters, or roughly 267 meters closer. 2,000 newtons has been expressed a distance of 267 meters. Energy is force times distance. 2,000 newtons times 267 meters is equal to 534.1 kilojoules. Most likely these results are correct. And the magic show ain't over yet. Left out of this discussion entirely is time. Suppose this shaft performs these certain number of revolutions within a given time period. This means the same amount of energy can be input to our system slowly or rapidly, and this time rate of energy change can be quantified. I'm of course leading up to a discussion of power. Power is not energy. Energy is not power. Power is equal to energy over time. Power is a time rate expenditure or production of energy. If you are still hazy about the distinction between power and energy, by all means check out the Energy and Power lecture available at the Big Bad Tech channel and clarify any remaining misconceptions. Here's an analogy. If you need to perform a certain task, it requires a certain amount of labor. Let's say you've got to stack a cord of firewood. A cord of firewood represents a measurable quantity of energy you put into a system. How fast you stack that cord of wood is your choice. If you knuckle down, shut up, and just stack the firewood in 30 minutes, you accomplish the task powerfully. If, however, you pick at the task, drag your feet, and bitch and moan about it over the course of 8 hours, you did it not so powerfully. More powerful input allows you to accomplish the same task quicker, whereas less powerful input required more time to accomplish the same task. It makes sense. Power is measured in units of energy per time, where 1 watt is equal to 1 joule per second. If you want to, you can package power up in some more readable arcane units called horsepower, where 1 horsepower is equal to 746 watts, or 550 foot-pounds force per second. Linearly, power is easy to conceptualize. Rotationally, not so much, albeit it's intrinsically much easier to understand than our earlier discussion of torque, because a rotational shaft is obviously rotating at a given speed or number of turns per given time period. If a shaft rotates slowly, yet it still exerts a constant amount of torque per revolution, chances are it's delivering less power to a system than one exerting the same amount of torque per revolution, but doing so at a greater rotational speed. The missing link in our discussion of power is this speed quantity, which some genius decided to represent mathematically with the letter N. Rotational speed is commonly expressed in units of revolution per minute, or its abbreviation RPM. Given a shaft with a radius r exerts a certain amount of torque for the course of 1 complete revolution, delivers 2 pi torque of energy per revolution, how quickly is it doing so? i.e., how powerful is it? We have the energy, we have a rotational speed. If power is equal to energy per time, the answer is quite obviously energy per revolution multiplied by revolutions per time. Units of revolutions cancel out, and you get energy per unit time. If, however, you stick with speed measuring units of revolution per minute, though, you'll have a major problem, because power must be expressed in watts, or joules per second. Therefore, we must convert RPM to revolutions per second by converting 1 minute to 60 seconds. Our final expression of mechanical power is energy per revolution, or 2 pi torque, times revolution per time converted to seconds, where mechanical power is equal to 2 pi torque times rotational speed divided by 60. Since 2, pi, and 60 are constants, pi being the irrational number 3.1415 blah blah blah, you'll sometimes see this formula written as power equals torque times rotational speed divided by 9.55. It's actually 9.54929 blah blah blah. There are all sorts of derivations for mechanical power, given foot-pounds of torque as an input and converting into joules, or given inch-pounds of torque and converting to joules, or given newton-meters of torque and converting to foot-pounds force per second, but they're all useless to you because you're not going to remember them, and I'm not going to make you remember them. The reason I'm not making you remember the different formulas is because I'm utterly confident in your ability to convert individual units at whatever level of abstraction necessary to get the job done. In summary, mechanical power in units of watts is equal to torque in units of newton meters times rotational speed in units of RPM divided by 9.55. Write this down in your notebook. Let's try some basic examples of this formula and its algebraic permutations. Consider an induction motor exerting 1.1 newton meters of torque at 1,736 RPM. Substituting our given torque and rotational speed value into the mechanical power formula demonstrates this motor is exerting roughly 200 watts, slightly more than a quarter horsepower. If this is the rated condition, i.e. the condition for which this motor was designed to operate, we'd most likely see this data specified in the motor nameplate. The rated condition for an induction motor is a single point on a speed-torque curve. Other operational points exist. Design B induction motors exhibit a characteristic speed-torque curve that looks something like this, where torque is plotted on the vertical y-axis and rotational speed on the horizontal x-axis. Consider the same motor at the no-load condition, an occasion in which the motor turns rapidly, let's say at 1780 RPM, but exerts zero torque. Substituting our given torque and rotational speed values into the mechanical power formula demonstrates this motor is exerting 0 watts of mechanical power. It makes sense. It's turning quickly, but not doing anything. Consider the same motor at maximum power conditions, an occasion in which torque and speed form a maximum power product. Let's say at the motor maximum power point, the motor turns 1364 RPM and exerts 2.1 newton meters of torque. Substituting our given torque and rotational speed values into the mechanical power formula demonstrates the motor is exerting roughly 300 watts. This is 1.5 times in excess of the motor's rated condition of 200 watts. However, as long as it's not sustained for any length of time, this 200 watt rated motor is capable of exerting a brief burst of 300 watts of power. Consider the same motor breakdown or maximum torque. On occasion in which the motor exerts maximum torque, however, rotational speed is slightly reduced. Let's say the motor is capable of exerting a max of 2.2 Newton meters of torque at 1,194 RPM. Substituting our given torque and rotational speed values into the mechanical power formula demonstrates this motor is exerting roughly 275.1 watts. We're clearly on the downslope of power now. Lastly, consider the same motor at the locked rotor condition, an occasion in which the motor exerts a respectable amount of torque, but it isn't moving. Let's say the motor is capable of exerting 1.4 Newton meters of torque at standstill. Substituting our given torque and rotational speed values into the mechanical power formula demonstrates this motor is exerting 0 watts. Makes sense. It's not moving. If we were to plot mechanical power, the product of torque and rotational speed divided by a constant for this entire rotational speed range, we'd get a plot that looks something like a rightward leaning peak. At opposite extremes, i.e. at the locked rotor and the no load condition, the motor exerts no power. And in between these extremes, the motor experiences peak power, or the rated power condition on the face of the slope on the right. This is an important operational point because customarily motors are operated at or near the rated condition. At the rated condition, the motor turns at the rated speed, exerts the rated torque, and produces the rated power. This is the data you would most likely see on a motor nameplate because it's normally the most efficient means of operating that particular motor, or nearly so. Anything to the right of the rated condition is an underloaded condition, and theoretically, the motor could operate indefinitely at or under the rated condition. In contrast, anything to the left of the rated condition is an overload condition and isn't meant to be sustained for any length of time. Moving on, let's compare and contrast three different styles of 200 watt motors. One having a rated speed of 3472 RPM, one having a rated speed of 1736 RPM, and another having a rated speed of 1157 RPM. How can all of these be 200 watt motors with such radically different specifications? The answer is torque. Mechanical power is a product of torque and rotational speed, and given the observed differentials in rated speed, one might expect different rated torques given identical power ratings. An algebraic manipulation of the mechanical power formula solving for torque demonstrates torque equals mechanical power times 9.55 divided by rotational speed. Substituting in our given mechanical power and rotational speed values for the first motor demonstrates the first motor exerts roughly 0.6 Newton meters of torque. Similarly, substituting our given mechanical power and rotational speed values for the second motor demonstrates the second motor exerts roughly 1.1 Newton meters of torque. Finally, substituting our given mechanical power and rotational speed values for the third motor demonstrates the third motor exerts roughly 1.7 Newton meters of torque. As these primitive graphics are meant to represent, the higher torque, slower speed motor also is physically larger than the lower torque, higher speed relatives, despite all of these being 200 watt motors. This example is meant to illustrate that different motors are designed for different tasks, and they're not necessarily interchangeable. Do you need light torque at high speeds? Use the first motor. Do you need high torque at low speeds? Use the third motor. Do you need a motor to regularly exert more than 200 watts? Don't use any of these motors. Use a motor that can handle the power requirement without risk of damage. Let's put your understanding of the mechanical power formula to the test with a series of illustrated example problems. Given the specified data, see if you can solve the desired unknowns. Some problems may necessitate unit conversion and/or algebraic manipulation. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. Our first example features a motor exerting 2 Newton meters of torque while rotating at 1760 RPM. We're being asked to determine the mechanical power in units of watts, and again, horsepower. Substituting given torque and rotational speed values into the mechanical power formula demonstrates this motor is exerting roughly 368.6 watts. A unit conversion demonstrates 368.6 watts is just shy of half a horsepower. Our second example problem features a motor exerting 2 horsepower of mechanical power while rotating at 1160 RPM. We're being asked to determine the torque in units of Newton meters. A unit conversion demonstrates 2 horsepower is equivalent to 1,492 watts. An algebraic manipulation of the mechanical power formula solving for unknown torque demonstrates torque equals mechanical power times 9.55 divided by rotational speed. Substituting our given mechanical power and rotational speed values into this algebraic manipulation demonstrates this motor is exerting roughly 12.3 newton meters of torque. Finally, consider a 3/4 horsepower motor with a rated 1.6 newton meters of torque. We're being asked to determine the rotational speed. A unit conversion demonstrates 3/4 horsepower is roughly equivalent to 559.5 watts. An algebraic manipulation of the mechanical power formula, solving for unknown rotational speed, demonstrates rotational speed is equal to mechanical power times 9.55 divided by torque. Substituting our given mechanical power and torque into the algebraic manipulation demonstrates this motor is spinning at roughly at 3,339.5 RPM. By the way, RPM is typically expressed without the use of engineering units. There is no such thing as 3.3 kilo RPM. Easy, right? Let's step it up a bit with 2 additional illustrated examples necessitating an understanding of efficiency, unit conversion, and power calculations. Follow along, or if you're up to the challenge, try them yourself. The properties of torque and rotational speed aren't limited to electrical motors, but can also be used to quantify the output of rotating mechanical linkages and other rotational actuators, like hydraulic motors. Consider a simplified block diagram of a modern horizontal axis wind turbine consisting of the hub and main shaft assembly, the gearbox, high-speed and coupling assembly, and the generator and power conversion assembly. This example will largely concern itself with a gearbox. Let's say at 12 meters per second, the hub is exposed to 5 megawatts of wind power, of which only 2 megawatts is transferred to the gearbox. Let's say the hub spins the main shaft at a relatively relaxed rate of 25 RPM. The gearbox is known to have a 1 to 50.4 step-up ratio with respect to speed and has an efficiency of 95%. We're being asked to determine the torque of the main shaft, as well as the torque, power, and rotational speed of the gearbox output shaft. First, let's determine the torque exerted by the main shaft. An algebraic manipulation of the mechanical power formula, solving for unknown torque, demonstrates torque equals mechanical power times 9.55 divided by rotational speed. We know the main shaft experiences 2 megawatts of input power and rotates at 25 RPM. Substituting these values into algebraic manipulation demonstrates the main shaft exerts an astonishing 764 kilonewton meters of torque. Given the gearbox is known to have a 1 to 50.4 step-up ratio with respect to speed, the output shaft should be rotating at 50.4 times 25, or 1260 RPM. Efficiency is equal to output over input. An algebraic manipulation of the efficiency formula, solving for output, demonstrates that output is equal to input times efficiency. Substituting in our given values demonstrates the gearbox successfully transfers 1.9 megawatts of usable mechanical power to the generator. Given known speed and known mechanical power, we can substitute these given values into an algebraic manipulation of the mechanical power formula, solving for torque, which demonstrates the high-speed shaft exerts roughly 14.4 kilonewton meters of torque. While we've got this example in front of us, let's talk about what's going on here. You'll note the gearbox is exchanging the low-speed, high-torque input for high-speed, low-torque output suitable for electrical power generation. Now keep in mind the terms high and low are only relative in nature. 14.4 kilonewton meters of torque is more than enough torque to rip your balls right out of your sockets if you or a piece of your personal protective gear or clothing gets tangled up in the high-speed shaft. It's for this reason shrouds are commonly used to cover rotational mechanical hazards. Additionally, consider where that missing 0.1 megawatt or 100 kilowatts of losses went. Did it just disappear? No. This power is going towards non-useful, destructive output, namely frictional losses, vibration, heat, and sound. This is why it's essential that a gearbox include not just the gears, bearings, shafts, seals, and housing, but also a means of lubricating and cooling these components. This 100 kilowatts of losses has to go somewhere, and the film of oil coating the moving gears not only eliminates destructive metal-to-metal contact, but also transfers the heat away from the mating surfaces. It's for this reason you'll sometimes see a radiator or a heat exchanger used to cool the gearbox oil and rid itself of this heat so the oil doesn't thermally degrade and the gearbox continues to function properly. This also explains why gearboxes are built out of heavy metal rather than compressed cheese. The housing must be robust enough to absorb and dissipate the losses inherent in its operation. Lastly, consider the efficiency of this complete system. One might be shocked to realize of the available 5 megawatts of wind power, the turbine delivers only 1.7 megawatts of usable real electrical power output to the grid. This is an efficiency rating of only 34%. This efficiency figure is something the gullible jerks of the world are quick to seize upon. My follow-up observation of this is, who cares? Wind turbines use free fuel. Yes, renewable energy systems are initially more expensive to install. And yes, they need to be maintained just like you would a gas generator or a coal-fired power plant. And yes, balancing intermittent distributed sources like solar and wind is more complicated than traditional centralized generation. But when the wind blows, the river runs, or the sun shines, as they are regularly known to do, renewable fuel quite literally falls from the sky. All you got to do is catch it. Who cares if you spill an armload if your planet is regularly bathed in it? But I digress. Let's check out another example of mechanical power, torque, and rotational speed.